sound is good. So Paul, apologies if that's still not good for you. Okay. All right, so today we're going to be covering blade flapping or hinging and how to avoid it. And just remember, please put comments down on the right here in the little comments section, and I'll address those as we go. Okay, so best start the slideshow. Okay, all right, so in this presentation today we will understand what blade flap is, understand why it's happening, understand what we can do to avoid it, how to recognize it if it's happening, how to recover from it when it's happening, and how to think about blade management in order to stop it ever happening in the first place. And we're going to be looking at the terms hinging and flapping, what's in a name. The way I was trained, it was always called hinging, and most of the world calls it flapping. So we'll discuss that, and then we'll have a quick Q&A afterwards. All right, so first thing to look at is Cierva's prototype here. This is one of Cierva's prototypes. He crashed several, and it was basically a Avro 504, and he was trying to, as most of us will know, trying to develop an aircraft that couldn't stall. And by having the wing spinning, it meant there was forward speed on the blade even if there was no speed on the airframe, and so he would avoid it stalling. Now you could see this first one of these first prototypes, 3-bladed. It's solid, it's got enormous blades, and he discovered that there was a major problem with controllability. Two problems actually. One was disymmetry of lift, which is what we're going to be talking about a lot today here, and the other was gyroscopic precession. The machine was uncontrollable. So if you've ever held a drill or an angle grinder and wobbled it about, you'll feel gyroscopic precession. He was experiencing, or his test pilots were experiencing that when they were trying to fly it, and it was basically uncontrollable. But the main problem he was recognizing, as soon as he got up to speed, the machine would lift and on the advancing side and tip over on the retreating side, and that was because there was a difference in lift between this blade here and the blades on this side, and there'd be more lift on here and it would tip the machine over. And so he had to figure out what to do about this disymmetry of lift. Now let's just explore the problem. The problem of disymmetry lift happens because the blade airspeed is different to the rotational speed. So the way I want you to imagine this is, I'm still on my first page, guys. Can I just get a quick, just going to make sure this is still, yeah, it appears to be going, but there's a massive delay in there. Can I just get a, sorry to interrupt this, but my live feed is still, I'm still like there must be a huge delay. Can I just get a hands, oh no, here we go, it is working. My apologies. All right, so the way I want you to look at this is, imagine you've got a radar gun and we've spun up the blades to 300 miles an hour, and we were able to measure the blade tip speed with the radar gun. The blue retreating blade here going in this direction with the wind is doing 300 miles an hour with the radar gun, and the yellow blade, if I was to measure it with the radar gun, would also be doing 300 miles an hour, and anywhere where I pointed that radar gun, the blade would be doing 300 miles an hour. Now the airspeed, however, is different. If I imagine this gyro flying forward at 50 miles an hour, or the machine stationary at 50 mile an hour wind blowing through it, then the actual speed of the rotor is combined with the speed of the airspeed. So I get a 50 mile an hour wind plus 300 miles an hour. So the advancing blade is producing 350 miles an hour. And because the air is moving in the same direction as the wind, it actually subtracts that 300 from that 300 miles an hour. So this one is 300 miles an hour minus 50 miles an hour on the retreating blade, and that means at this point here it's doing 250 miles an hour. So it's always double the forward speed difference between the two blades. So if I had 100 miles an hour airspeed, this would be 400, this would be 200. And you can imagine the difference in lift between the two blades. Remembering that that lift is going to be massive therefore on this thing. And if this hub was fixed, if this hub bar was fixed and couldn't teeter, then that would tip the whole machine over towards the retreating side because it's just producing that much more lift. Now, Sierva was a civil engineer before he became a aeronautical engineer, and he'd worked on things like bridges and was familiar with some of these structures. Now, this is the base of the Sydney Harbour Bridge. The Sydney Harbour Bridge in Australia gets quite hot and it cools down at night. So a lot of these metal bridges will have these sorts of hinges in them here, and this is a hinge to compensate for the expansion and contraction. So as the bridge expands in the day, this whole beam actually lifts up because it gets bigger and bigger, and that hinge allows it to hinge up without putting stress on this joint. At night, when it cools down again, it will contract and fall back down, and again that hinge relieves the stress. Sierva realized that the blades were in a similar sort of situation. They had to dissipate their extra lift on the advancing side and allow the blade to fall on the retreating side. He realized that that was something that should be tried, so he put a flapping hinge on his rotors. And this is what the flapping hinge looks like on the multi-bladed rotors. So you've got the fixed hub bar here section, and you've got a hinge here which allows the blade to flap up and to flap down. So on the advancing blade it would flap up like this, on a retreating blade it would flap down as it went around the other way. Now, the reason that works is that there's two ways of producing lift. One is airspeed, and the second is angle of attack. Now, the way to think about this, and I always find it harder to think about with the blade flapping up than the blade flapping down. So just, if you imagine you put your arm out and you were to hold onto a ribbon at the end of your arm, and you were to spin yourself around in a circle, the ribbon's going to be pointing backwards. But if, as you're spinning around, you move your hand down, the ribbon will point upwards, increasing its angle of attack. And if that's what happens when you're pointing it down, as you bring your arm up, then the angle that your ribbon is going to go is going to be reduced. Now, the fact is the blades have a positive angle of attack. They're angled back at 9 degrees in flight. So they still have a positive angle of attack on the advancing side, but it reduces the angle. So two ways of producing lift: airspeed and angle of attack. So we're going to have a look at this here. So this is the simple motion, and we're evening out that angle of attack and airspeed. So in our simpler blades, we have a fixed blade going through here, and this teeter hinge is more like a seesaw than the flapping hinge, which has two. On a flapping hinge here, you'd have a joint here and a joint here, allowing them to flap up and down, and this would be stable. But the flapping hinges, we just have one seesawing, teetering blade. And basically that means as the advancing blade comes along, it's lifting up and it's pushing the retreating blade down. So remember, there's two ways of making lift: airspeed and angle of attack. Increase angle of attack, you increase lift. Reduce angle of attack, you reduce lift. Increase airspeed, you increase lift. Reduce airspeed, you reduce lift. So the two actions that are happening: as this lifts up, it reduces its angle of attack and reduces its lift. This one at the same time is being pushed down, increasing its angle of attack and lift by increasing its angle of attack, even though it's losing its airspeed. So the two end up, while they're teetering, having identical lift on either side, and therefore the disymmetry of lift problem is solved. It also solved the gyroscopic precession problem. I won't go into why that is, but the gyroscopic precession is not an issue in the gyros because of that teeter hinge. You can ask about that in the questions if you want. All right. Now we can have a look at this from another view. So if I'm looking at this, this is would be the front of the gyro, moving 50 miles an hour into the wind. The blade is turning around this way, and in this case 300 miles an hour, which means at this point this is teetering up, this is teetering down, and if we look at it from directly front on, that's what the blade is doing. Now this is all exaggerated. Most of these diagrams I'm going to be using today are exaggerated. In fact, if it was this far here, I would be exceeding the teeter stops. But that's the idea. This goes up, that goes down. Now, this is from the Benson Design Classroom series. Benson wrote a number of technical articles in the early PRA magazine, and they were compiled together in the Benson Design Classroom. Strongly suggest any of you have a look at these and have a read through these. A lot of people don't realize that Benson was an aeronautical engineer. He didn't just bodgy up a small lightweight gyroplane. He actually knew what he was talking about. This is one of the diagrams he used for regular flight. So this is at 50 miles an hour in one of his machines. And you can see the angle of attack distribution going around here. And so as the blade is going into the advancing side, you can see these are very low degrees. In fact, at this point here, the angle of attack at the tip of the blade becomes negative. All right, it is actually negative angle of attack, positive in here. And the retreating blade, because the airspeed is so low in here, it actually goes and the angle of attack gets so high, but mainly because you've got reverse airflow, this whole section is stalled, and then you start getting a positive angle of attack here. Now, we're looking at 6 degrees in this zone, 8 degrees in this zone, 10 degrees in this zone, 12 degrees in this zone, and 14 in this zone. So, I want you to also have a think about this. A lot of gyroplane CFIs will talk about driven and undriven areas. This kind of makes that a bit of an untruth. This area here is not at all driving this outer section here, because this is literally producing zero lift. There's lift being produced in the inboard section here, and this outboard section here, I suppose you could say, is being driven, but that's not true here. Along here, the whole up to about here, this whole section is driving the blade, because this has no lift. So it's not as simple as saying there's an inboard section that drives the outboard section. In fact, the early Cierva gyros, I tried to find a photo of this, but one of the first successful gyros that Cierva flew had only like 4-foot stubs of wings out the tip of a pole. So he only had the outerboard section producing lift and no inboard driven section, and they were still auto-rotating. In fact, some of the early gyros like this had a similar sort of arrangement where they had almost no aerofoil section on the inboard section here, and that was basically a drag reduction exercise, and most of it out here. So it's not quite true. It's an oversimplification. Anyway, back to angle of attack. All right, this is a situation where we develop blade flap. Now, the reason this is happening is, for example, we might have 3 degrees on this side, but if the retreating side is producing 16 degrees or more, because the blade is in flap, has exceeded the 16 degrees, or at 16 degrees, this blade will be stalled. And you got to remember from that diagram, this inboard section stalled anyway. So if we stall the outboard section, effectively the whole rotor on the retreating blade stalls. And that's what blade flap is. Blade flap can simply be thought of as a stalled retreating blade. It's producing more than 16 degrees of lift on the inboard section that has reverse airflow, and is probably also exceeding 16 degrees of angle of attack, not lift, sorry. And so the blade stalled, it's producing no lift. So everything that then follows from what we see as blade flap and the behavior of blade flap comes back to this fact. The advancing blade has plenty of lift because it's got plenty of airspeed. It lifts up, pushes the retreating blade down. The retreating blade, if it gets to the point where it exceeds 16 degrees, will stall, and that's where our chaos ensues. Okay, so simply put, blade flap occurs when the retreating blade stalls. The exceeding the teeter stops is happening simply because the retreating blade stalls. It's not we've exceeded the teeter stops. Now, if you exceed the teeter stops because you've put too little teeter stop in, it can exceed the teeter stops before it stalls and give you blade flap type problems. But it won't be the same level of problem. It will give you a stick shake in flight, but it's not going to be the same problem as it would be if the blade is actually stalled on the retreating side. And we'll get into that in a little bit more detail. But the way to think about this is blade flap is just retreating blade stall. The retreating blade has exceeded 16 degrees angle of attack. It therefore has zero lift. All right. Now, what happens as we've got the blade is in flap and it's reached the fore-aft point of the blade. Now remember, blade flap is typically happening when you are winding the blades up. So our blades are actually exceeding the teeter stop, and our blades are usually full backstick because we're winding our blades up. Now I want you to think about what this means mechanically. This teeter hub here has hit the teeter stop here. It's locked out. Mechanically it can't go any further. This is at full backstick, so the torque tube is touching the rear stop, so it's fully locked out. This is attached to the cheek plates, which are attached to the mast, so it's fully locked out. So the whole thing is mechanically fully locked out. And yet, anyone who's gone through blade flap will tell you that your stick starts to shake violently around. How can our stick be shaking violently around? What is the mechanism by which that actually happens? Well, for that to actually happen, you actually have to be bending the whole mast back and following the blade around violently for this to happen. Because remember, this blade is already at the rear stop. This one's at the top. It's got lots of space, but as soon as this one moves a little bit further around, it's now going to stall and fall back into this position. So you get this rhythmic cyclic bending, and the whole mast is swinging around in quite a wide arc. That arc it's moving in is moving the control rods here and here, and they are attached at the bottom. They're basically fixed to the bottom of the airframe, and that means that the stick is following the control rods. The control rods are only moving because you are moving the whole mast. Think about the forces involved in that for a minute. Think about how dangerous that is for your airframe. Think about all these joints, all these bolts, all the control rods, particularly in this. If your control rods fatigue and break or bend, you're stuffed. If one of those comes off in flight, how are you going to control the gyro? So the stresses you are putting on the machine with that is immense. So please think about the actual what's happening if you allow it to get that far. Okay, now if you let blade flap develop, and if you're ever at the side of the strip watching a gyro in severe blade flap, you get this S shape. Now this is obviously a pretty massive exaggeration in that it's a cartoon, but believe me, you will see that S shape, and if you've ever seen it, you will not forget it. Blades that are in massive flap going up and down the strip will form this giant S shape. This is going to come back later when we talk about some of the accidents that are presumed to be blade flap but are not. But the reason this happens is you've got the blades are flexing and violently transitioning between these. This has no lift, so this falls to the ground. This has heaps of lift, so it swings way up in the air. And you will get this S-shaped bending, particularly when you're watching a powered machine going past you up and down the strip, or a gyroglider going past you. When we were training in the gyroglider, we would be standing, most of us would be standing on the side of the strip, a couple of people in the car, and the driver, but the rest of us would stand at the side of the strip waiting our turn. And if the blades develop flap badly enough, this is what they look like. They don't look like this initially, but they do look like this eventually. And it's about now, when they're getting to this sort of shape, that they'll chop off your tail, hit your prop. If you think most gyros have some clearance between the prop and the rotor, even at full back stick with fully teetered, they'll have some clearance, and yet the blade will bend down far enough to hit the prop. Okay, now this is what it looks like from the outside. This is gyroglider at Wandai. I'm not having a go at the club members here that allowed this to get into blade flap. It can happen to everyone, particularly when you're in the gyroglider. If you get a driver that takes off a bit too excessively fast, or if the driver is driving normally but a thermal kicks off or a gust hits, you can get into blade flap pretty easy. And about 2 seconds later in this shot, this instructor here puts his hand out to indicate that the blades are in flap. But the observer should be noting, now what I want you to note is, look how close this rear blade is to the deck here. It is inches above the airstrip. So it's within inches of destroying those blades. If it hits that dirt, that's it. The blades are smashed up, possibly the gyro rolled over. He was able to pick it up and save it, and then a few seconds later in the video, this is what we got. So they put in an edit in the video. These blades look bent. They're not bent because they're in blade flap. They are spun up normally. This is just a shutter effect of the shutter speed of the GoPro camera. But you can see when the blades are producing lift, they cone up, and even at full backstick, that's the distance between the ground and the tip of the blade there. I'll put that arrow in to show that. They're both coning up, and so it's about the height of the top of the seat where the blade is at full backstick. They're about to take off, so they're still full backstick here. Alright, so that's not flapping, but you can see the difference. Alright, so this is a bit of a cartoon version of the same thing. If you're in the gyroglider, what are you going to see from the car? This is pretty good and normal. The blades are spun up. They will be lower than this, maybe to about here. They will be lower than this when they're winding up properly. But if you see anything like that and you're observing in the car, that tells you the blades are in flap. You need to get the car to slow down and communicate with the instructor that their blades are likely to be in flap and they should check. Now, if you're in a powered machine, the instructor in that glider could not see how low those blades were at the back because he's facing the wrong way. So this is what you're looking for out the front. Now this is true of a powered machine as well. So this is what you should all be looking for in a powered machine to make sure that you're understanding whether your blades are in flap or not. Now obviously you don't have a big yellow disc. I'm just showing this to show the path that the blade normally takes. So if the blades are winding up, they will appear to make a nice circular path in front of you like this each time as they spin around. If they are in flap, remember, the advancing blade over here is starting to lift up and it will reach its peak about here. It'll get to its highest point, and then once it gets over to here, it's losing its airspeed and it's being pushed down, so it will go down. So what you'll see is this. And this is, I've done this accurately. This is as subtle as it will be. It can be more extreme than this, but if you can pick it when it gets to here, then you can actually start to pick up before you start to get any stick shake. So what it will do is swing up to here and then swing back down, swing up, swing down, and it will kind of whoosh up, down, whoosh up, down. It'll seem to sort of accelerate up and down. If you can see something like that, and the blades will still be spinning quite slow at this point, if you can see something like that, you need to be ready for the fact that the blades are probably in blade flap. It's subtle. It takes time to learn to see, look at what you're doing. But this is my point, is I think rotor tachos are risky. I'd happily fit one out of interest, but it's if you're spending your time looking at the rotor tacho, unless your rotor tacho was also measuring airspeed, and there was some sort of needle system or something where you had two needles so that when they crossed over to a certain point, the blades were in flap. What you really need to be doing is looking at your rotor. Because if you can look at your rotor and know what you're seeing, feel the breeze on your face, look at the rotor. If you have a cabin, then be looking at your indicator to see if there's any change in wind speed. It's not ideal. It's actually better if you've got an open frame gyro for this sort of thing. But if you can learn to see this, you will save yourself from blade flap. Now, if you see something like that, or if in doubt, or if you just think your blades are not coming up to speed fast enough, then what you need to do is push your stick off the backstop. So just push the stick an inch forward, and then if you feel the stick starting to aggressively go into cycles at that point, you know you're in blade flap. Why this works, remember we were explaining when the stick was full back here, it's all locked up. If you lift this off the back stick, then as that blade hits that backstop, it's going to push the torque tube down, and that's going to move the stick for you. So pushing that forward will show you that the blades are flapping before they get too aggressive and before they risk smashing on the ground or smashing on the rudder. Yes, Brian's referring to the rotor RPM gauge. Yeah, that's what I was referring to, a rotor tacho. Okay, so if we're in blade flap, what do? We push full stick forward at this point and we cut power at the same time. Do not push full forward, stick forward, then cut power, then push full, just both at the same time. Get that stick forward, excuse me, get that stick forward, cut the power, and then start again. Why this works is we are trying to remember the blade is stalled on the retreating side. Our basic fundamental principle is the blade is stalled on the retreating side. We have to unstall that blade. We unstall the blade by reducing its angle of attack. dropping it from 16 degrees to 14 or 12, so it's producing lift and starts to cone up again. So pushing the stick forward reduces the angle of attack of the blade. Cutting speed removes your disymmetry of lift. Remember, the disymmetry of lift is happening because of the difference between the airspeed on the advancing blade and the airspeed on the retreating blade. So when you remove the power, cut your speed down, you reduce disymmetry of lift. When you push the stick forward, you reduce your angle of attack. Both of those things will stop the thing from stalling. So removing disymmetry of lift means the blade's teeter less, which means that also reduces the angle of attack on the retreating blade. So just to go over that again, the retreating blade is stalled, which means it has too high an angle of attack. It's stalled because of the airspeed difference between the advancing and retreating blade, which is causing excessive teetering to occur, hence the stalling. So full forward stick removes the angle of attack from both blades, which are now neutral, and reducing airspeed removes the difference in lift between the advancing and retreating rotors. That's why that works. Okay, so how do we avoid it in the first place? So the thing we want to do is to start fast, go slow. Now, in modern gyros, there's a different way that they are attempting to avoid blade flap, and I think these lead to further problems, which I think are a major issue. And a lot of the modern machines, they will typically spin up the blades to 220 RPM or some over 200 RPM. Then they will, in a very short space of time, apply full forward power and full back stick at that point. The idea being that while the blades may decay from 220 to say maybe 200 or 180, their idea is to stop, to get the blades accelerating again before they run the risk of getting into blade flap. Blade flap in the early days when I was learning to fly was a significant issue if people weren't taught to do it properly. And I say if people weren't taught to do it properly, it was not a significant issue. It could be picked up, you can learn how to do it, you can learn how to do it properly. The danger you have is in people getting out of sequence. If they forget something, if they forget to pull full back stick in, or they do things like that, they can cause blade flap with the modern approach. And if they do, it will happen at 30 or 40 miles an hour instead of 8 to 10 miles an hour. And obviously it gets more serious when you're doing it there. And there's also a problem of over rotation that happens because everything is now rushing together and happening very quickly. So remember the basic fact though, that we're the difference in advancing and retreating blade is always 2 times the forward speed. Remember too that the teeter hinge is compensating for the difference between the advancing and retreating blades. So the more difference, the greater the teeter angle. So we're going to have a look at a bad example here.
Okay, this is Erskine Park back in the
as
early
you go through,
days
see
of
if you can
gyroplane
pick
flying.
up any of his mistakes.
And this guy's about to do pretty much everything wrong
Let's go have a
you
look at
can
the comments.
do in setting up your blades. See
Already
if
there's been a
your
mistake.
comments
See
can
if you
pick
can
up,
pick that up. Feel free to
some of
comment
the
in
mistakes he's
comments
making.
anything
Just
you
type
see
into the
here.
comments as you go.
He's got his motor running.
will
That's the
tell
right
you.
thing to do.
I'll give you a little bit
He
of
wants to
delay
warm up
though,
his engine.
and,
It's a V-dub, so he's
see
not
how
got an
many of them
electric
you
starter,
get.
so you can't be
I
warming
will
up
tell
the
you,
blades
run
and
through
trying to
some
kick over your
of the problems
blades.
he's having at the moment, Dave.
But he's
So for
made
a
a
start,
mistake already.
you should
Not too big
have
a
your
mistake
blades
yet.
forward and tilted down. It's not
Basically,
too much danger when the blades
no
are
one's
stopped.
picked up on the comments, so
But
I'll
really
just
you
tell
can
you,
actually have the blades flick
allowing
around
the
at
blade
wind
just
and
freely
all sorts
flop
of
around
things, so
like
you
this,
really
they
shouldn't
can
leave the
start
blades
moving, they can
untended.
get blown about by the wind.
He's now
There can be big problems
starting to
with
spin
that.
the blades,
Now,
but his stick
already
is
he's
full back.
taking off, he's got the
And
stick
again,
full back.
as soon as you do that,
Any
and
speed
you've
at
got
all
some
you
headwind,
give these blades
you're
with
in,
the stick full back,
blade flap
or
territory.
with it sitting on its tail, is going
And so
to
he's
leave
using his
you
foot
open if
as
there's a
a,
breeze to blade flap. And he's not in much of a position to actually
stop
do anything
for the
about the
blades.
blade flap.
Just watching another guy.
Oh,
doing
I've
his
put sound on
taxing.
this.
is
I
how it was
apologise,
all done
guys.
in the old days. Fortunately, these guys don't have a decent instructor. Otherwise, he would have been told off about 3 times already. He's now winding every blade up until they're too fast. This is all okay. He's got his right hand on the mast, cheek plates actually, if that's okay. He's now going to every second blade. You can see the nice little stops there to stop the teeter. Their teeter stops sort of soft. They've got like spring steel and nylon. Now here's where he starts to screw up real bad. Blades fall back. What's he do? He's fluffing around. Put that bungee cord around me. Meanwhile, my blades are slowing down. Now, get into the seat. Let's have a look. Yeah, fidgeting around. He's not ready. Where's my seatbelt? Okay. Meanwhile, what's happened to the rotor speed? He's just lost there. All right. I haven't put my seatbelt on. Oh, I better put my seatbelt on. Okay, let's check the controls. Okay, I should have done that before I even started up the blades. Now look at how slowly those blades are going. Now he's moving forward, hands not on the stick, and still hasn't sorted out his seatbelt. And so his blades are free to sail there. Any gust comes along, those blades will be in blade flaps straight away. And there is no way he's getting those blades up from that speed. Finally gotten his seatbelt ready. So always get your seatbelt ready before you get in the seat. As soon as you jump in the seat, seatbelt straight on, start moving straight away. And there's no hope in hell he's getting those up. Now, they don't show the whole development of the blade flap here, but you'll see the disc get quite low. It doesn't develop the big S. They can develop that big S, but he's about to try and take off with that. Now you can see immediately the blades are stalled, so they're starting to get lower and lower, and you can see they're sailing closer and closer to the rudder at the back there.
Alright, my apologies for that, guys. I should explain, when we were testing this we were getting audio problems, and I think there was problems with streaming the live video from YouTube, so I put it on and put a narration on, and unfortunately I forgot I'd put the narration on and just started speaking over that as it was going, because I haven't got headphones hooked in here, because it confuses me to listen to myself echoing back 10 seconds later. Alright, so you can see some of the problems that happen, and this was typical of when people were teaching themselves how to fly and didn't understand blade flap, and were trying to teach themselves how to fly without fully understanding what they had to do. He did just about everything wrong there he could have done, and in fact later in that video, if you find the video online, he actually crashes the machine. So they clearly didn't have an instructor there, or he's probably doing this without any training, probably not even gyroglider training, unfortunately. Alright, now let's look at a scenario here. We've got blade speed as measured by the radar. Let's imagine we've got very low blade speed, 100 miles an hour. Now that's not going to be that unusual. If you're hand winding your blades up, they're not going to get that fast at the tip. You might be able to get them to 80 RPM hand winding. And imagine your airspeed is 50. This is not a good situation. So the advancing blade is 100 miles an hour plus 50, 150 miles an hour. A retreating blade is 100 mile per hour minus 50, which gives us 50 mile per hour, which means, of course, double the forward speed is 100 mile per hour. So that's an airspeed difference of 200 miles an hour between the advancing and retreating blade. So the advancing blade is 200% higher than the retreating blade. Okay, so the blade speed in scenario 2. All right, this time we have a much more moderate airspeed, 100 mile per hour here, an airspeed of 10 mile per hour. So we got 110 mile per hour on here, which is 100 plus 10. 100 minus 10 is 90, so that's only 122% difference. So you can see the strategy of starting off slow, but starting off quick. Get moving fast, but don't move fast. Get started, I would always have my seatbelt, for example, in the situation we looked at in the video above. I would have my seatbelt ready to go. I would have fitted myself in to make sure I could fit and I would only do the lap belt tight, and I'd leave the shoulder straps loose, the harness straps loose. And what that meant is that I would have my stick lock on the stick. I would have a stick lock to hold the stick forward. I would have my engine running behind me, and then I would bat up the blades. And then I would very quickly jump in the seat, put my lap belt on so I wasn't going to fall out, and start moving straight away with full back stick so I could start winding up the blades. Now, it's going to take you a little while to wind up the blades, and usually I'll be doing this in the taxiway leading up to the main airstrip. And while I am winding up the blades, I'm putting my left arm in the left harness and then pulling that tight, and then changing my hand to the stick on the other side, putting my right hand into the harness, coming around, holding onto the stick with the left hand, putting that harness tight. Not letting go of the stick at any point during that, watching the blades the whole point doing that. I rehearsed doing that. So as soon as I had those blades wound up, I was in the seat as quickly as I could possibly be. I had to stick back and moving forward as quickly as I could possibly be, having only secured my lap belt tightly, because it meant I wasn't fiddling around trying to quickly get into the thing, because any time you waste moving forward. Now, if you have a pre-rotator, you've already got the engine going, you pre-rotate up, and then you just start push the throttle forward and start moving forward straight away. Don't flummox around on the ground wasting time, or you're losing your blade RPM. All right, that's the key. Start fast, go slow. Don't go too fast. Now we're going to look at another scenario. Now this would be maybe the sort of thing you think, okay, well, why not avoid blade flap? So why don't I wind up my blades to a very high RPM rate, so let's say 200 mile per hour, and then I'm going to taxi forward at 10 miles an hour. Now you can see I've that makes that 210 miles an hour, 190 miles an hour, and that's only a difference of 110%. The advancing blade over the retreating. That's obviously not going to be teetering much, but there's a problem here. And the problem is I'm not going to be able to sustain 200 mile an hour tip speed at 10 mile an hour. The blades won't naturally be that fast at 10 miles an hour. So what I'm going to do is I'm either going to watch the blades decay in speed until they reach the speed at which they will naturally spin at 10 miles an hour, or I am going to accelerate up until I reach the point where the 200 mile per hour tip speed is maintained and accelerated up on, and that's where we reach a couple of little problems. All right, problem number one is I'm burning up airstrip going too fast. If I go faster than the blades are going to accelerate up to, or I'm trying to catch up to where the blades are at, I've got to use a certain amount of distance on the runway just to get up to that speed. And instead of doing a shorter runoff but slower, I'm doing a longer runoff but quicker. Now, I can't use the airstrip behind me, so the most efficient way is to spin those blades up only to the speed where I need to get them up, and then to just use airspeed to get the blades to naturally accelerate up to where they need to go. And I'll show you a couple of videos to demonstrate how well that works if you do that technique properly. The modern technique of trying to avoid blade flap at all costs, I think, makes people focus too much on the rotor RPM gauge and or the rotor tacho, and stops them from actually observing what the blades are doing. And if conditions change, or if they stuff anything up, they're vulnerable. And I'll show you a video on that too.
Okay,
this is an example of it being done badly. This is one has been blamed on blade flap, but it is not blade flap. All right, I'll explain why it's not blade flap. We're going to watch this. Oh, I'm doing it again.
Blade disc very far forward. This would risk blade flap, but I don't believe this is actual blade flap. He then pulls the blades back, and I believe here he's over rotated. What makes me think it's over rotation and not blade flap? Well, remember what I told you about blade flap being retreating blade stall. If you look at the moment that the accident happens, you'll see both blades are coned up and both main wheels are off the ground. How could your main wheels end up off the ground if your one side of the disc is stalled? So you can see here both blades both main wheels are off the ground, both blades are coned up. No way both those wheels got off the ground with that as blade flap. Unfortunately, in our sport, a lot of people blame this on blade flap.
Okay, again, sorry. I'm going to have to leave my headphones in, I think. It's the only way I'm going to make sure that doesn't happen again. Yeah, so as you can see here, I think this is a symptom of, this guy was obviously trained by a commercial CFI. I'm not suggesting the CFI was incompetent. This guy might have been a long time out of the air and then gotten back in and forgotten. But it's clear he doesn't really understand what's going on with the blades. And the process he's going through to wind up the blades means that error he made by holding the stick too far forward or forgetting to pull it too far back led to that consequence. And he didn't realize until too late, then hauled it back and then hauled himself off. Unfortunately, because many people don't fully understand blade flap, they will attribute these accidents to blade flap and then talk about blade flap in relation to this happening. Yeah, he was at risk of blade flap, but because the blades were so fast, when he did pull it back, the inertia in those big heavy blades meant that they didn't flap. He actually didn't get them into blade flap. They would have made that giant S shape. They would have not been coned up at the back. You wouldn't have lifted both wheels off the ground. That was simply over rotation. But it's over rotation happening because the way that most modern instructors will teach is to teach this method of winding up, which results in people actually very often getting into an over rotation situation. Getting behind the power curve is another problem with this rushed takeoff. and it doesn't necessarily save you any distance. Everyone thinks it saves you enormous distance to take off this way. It doesn't necessarily save you that much distance, and we'll have a look at that in a bit as well.
Okay, this is video of my friend Steve Cobden, who's sadly no longer with us, not gyro related, but this is around the time I was learning to fly. And Steve here is getting his blades wound up by Dennis here. You can see he's grabbing every blade, and there's been an edit, but Steve would usually sit and let the blades get as fast as they could in the prop wash of the rotor. So you can see he's not taxiing very fast here, and this was not a very high wind speed day. And you can see already the blades have come up quite fast. And he's just keeping it straight on the runway there. And already he's balancing on the mains. And this is the taxiway, not the strip. The strip is that grass thing in the distance. And off he goes. So you can see here that the amount of runway required when hand winding the blades, if you do it properly, so that's the start fast, go slow. You can see how slowly he was going at the start of that video. Shows you how to successfully wind up your blades. Okay, we'll leave him there.
Okay, so you can see that I've not seen footage of a Calidus or one of the modern machines get off that quick without a 15 to 20 mile an hour headwind. You can do it. It's a very light machine and there's very short blades, so those things contributed as well. If it was longer blades, he would have had a hell of a lot of time to get those up. They were 22-foot blades on that machine, and Steve was quite light as well, but you could see he had no problems getting those blades up to speed. It was progressive. It was a gentle procedure. It wasn't a sudden full power gun it and go, and now the blades, the nose is finally coming up and I'm having to struggle to maintain wheel balance and take off flat. Now, just to show you that the prop wash does actually have an impact, this was an early Cierva, and they used to originally wind a rope around the rotor blades, and 5 blokes would run out in a particular direction to spin the blades up, and they would have the stabilizer tilted over like this so that it would actually brush up air up through the rotor, and then there was a lever that they pulled it flat to get the prop wash from the tractor gyro up through the rotors to help spin up the blades. So it does work to some extent. You very much notice this when you're flying in the gyroglider, and the blades take a lot longer to come up than they do in a powered machine. Alright,
okay. In this video again, we've got a guy hand winding the blades. This guy's obviously a bit of an amateur. He should have a helmet on. He shouldn't be holding onto the control rod, or looks like he might be holding onto the pre-rotate cable. For some reason they're not using the pre-rotator. It might have a broken mechanism in it. Again, like Steve's video, he is going to be using this prop wash to speed up the rotor blade here. And you can, I put an edit in this to cut out most of this, but you can see it's starting to accelerate the blade, but he does this for a few minutes. So, and you can see already it's started to accelerate the blade. Now, when you look around later, you can see there's a tiny bit of breeze, but not much. If you look at the guy's shirt, he's winding up his blades, you'll see there's not much in the way of breeze, and if you look at the windsock later on, not much. Yeah, there's a flag that's blowing a little bit, but there's not much. You'll be lucky to find miles an hour here. Now, this is the cut that's happened here, which is why the blades have cut up, and he's about to do his takeoff. Now, the thing I want you to note here is how slowly he starts his takeoff run. He doesn't gun it to full power straight away and try and catch the blades up. He is trying to build the blades up gradually by watching the rotor speed, which is more than enough to make a start now. And he's about to take off. So you can see how little his shirt's moving. If that was like a 15 mile an hour wind, he would be, his shirt would be fluttering around quite a lot there. So there's not much wind there. A little bit, not much. And again, he's taking off on the taxiway of the airstrip, not on the main airstrip. Again, a bit risky this, but there you go. Again, not hauling too fast, and you can see the blades are picking up. and he's not trying to go any faster than that until the blades have picked up their speed, which is about now. He's now hitting at full power, balancing on the reins now, and lifting off just before the end of that taxiway. So quite risky, but there you go. About 100 metres. No pre-rotator. No blade flap. As you scroll around here and we get around to the other side, you can sort of see the windsocks pretty much limp. There is a bit of a breeze blowing on the flag, but not enough to lift the windsock up. A little bit of time in the windsock. So a little bit of a breeze, but it wouldn't be more than 5 miles an hour. Not enough to lift the windsock. And we'll just stay here for the landing. So this is a skilled pilot. This is a guy who knows how to avoid blade flap, knows how to watch his blades, knows how to not just play it by the numbers, but knows how to actually gauge the speed he's adding based on the speed that the rotors are at. Setting up for his landing. And a nice low speed landing as well. Okay. Okay, so that's that video. Alright, so the idea of start fast, go slow. So slow build up, gradually increase the you're basically gradually trying to increase your speed so that you're keeping your retreating blade angle of attack as low as possible. That's the goal. So building rotor speed slowly means you're controlling the retreating blade angle of attack, and you're waiting for the blades to accelerate so that the angle of attack doesn't get too high. So I'm giving you some speeds here, but just be aware those speeds will be different if you have different angles of incidence or longer rotors. So you can't rely on these speeds. You're going to have to figure this out. But for a machine like the ones you've been seeing, this would be somewhat typical. And really, I do this by feel, just feeling the breeze on my face. I know how much breeze I have. And this is one of the benefits of the gyroglider is it teaches you those feelings. And so while I have paid attention to the airspeed, I don't look at the airspeed gauge to do this. I just feel the rotor, feel the breeze on my face and look at the rotors. Alright, so if you're starting about 8 to 10 miles an hour, this is going to vary by angle of attack, diameter, rotor profile. The blades will start accelerating if they seem to start accelerating. If they don't seem to be accelerating, it could mean two things. You either don't have enough airspeed or you're close to blade flap. If you push the stick off the backstop and they're not in blade flap, then you know it's probably not enough airspeed. You may have to go out and wind them up again if you're doing it by hand. If you have a prerotator and a power machine, it's a lot easier, as I said, because you've got engine revs. I'm not suggesting people sit there for 10 minutes winding up the blades in the prop wash. I was just making a point with that. Typically I would actually just start taxiing. Once I got the blades up, I would start taxiing and just being aware that the prop wash will have an effect on that. Alright, when they no longer increase, so if I've started the blades up at my 8 to 10 miles an hour and they start accelerating and they stop accelerating, then usually that's time for me to just add a little bit more speed on and they'll start accelerating again. You learn to sort of do it. I've got enough speed now to go to the next stage, but you've just got to be very careful on all stages along here. Alright, and they will start to rapidly accelerate once they get into this second rev range. They pick up quite quickly there. Once you're getting up to there, then what you'll find is the machine will actually start to slow down on you if it's a powered machine, because the blades will now be producing enough drag, and because the disc is full back, it will actually start to slow you down. You'll find you have to increase throttle. At that point, you don't have to worry about blade flap. They're not going to flap. The blades will be hooting along, they'll be alive, and you're not going to get into blade flap, and you can apply power. Usually about 16 miles an hour in a little machine like a typical Benson or my VW Benson or a Gyro B or a two-stroke Rotax powered Benson. Around about 16 miles an hour you notice a lift,
and at that point you're quite free to put on full power and take off, and you won't have to worry about blade flap again until you've landed. Now, after you've landed, I always try and keep my blades up to speed while I'm taxiing back, simply because I've got control with the blades. The blades are producing lift that I can manipulate left and right, and so I can, you know, sort of adjust things as I'm going, and I also don't have to worry about blade flap if I keep sufficient speed to keep the blades spinning. They'll have heaps of inertia, and they will slow down, but if I keep them up to about 10 miles an hour taxiing, it's slow enough for the taxiing to be safe enough, and as long as I'm, you know, being careful about things like crosswinds and stuff. If I put a rotor brake on, you really want to be off the main runway on the taxiway, and ideally, if you're putting a rotor brake on, you have to be very careful, because with a rotor brake, they're still going to go through a phase where they're going to be at risk of blade flap. So if you're taxiing back, you're probably taxiing back downwind, depending on the direction. But even if you're not, if you put a rotor brake on, they're going to go through that phase where they're going to be at risk of blade flap. So you need to keep that blade forward. If there's a crosswind, you need to keep the disc pointed into wind so you don't get blade flap. I personally, if I had a rotor brake, which I don't, wouldn't use it until I was about ready to stop. So I personally would keep the blades up, treat the machine as a flying disc the whole time that the blades are turning, and where I would be shallowing out my disc to zero would be when I get into the parking area and I'm around other aircraft. At that point, I'm going to put the blades right forward, possibly stop at that point, let the blades decay down at least until a speed where I can see the blades just slowly going around and can really accurately judge where the tip of the blade is in relation to any other aircraft or gyro I might be parking near. Or at that point, I could get out, stop the blades, tie them down, and then taxi the rest of the way back and park near someone else. No one wants someone's machine being hit by rotor blades, their Cessna or their other gyro rotors being hit by someone's rotors because they're taxiing with their blades spun up. If you're in a really heavy wind, just be aware you may actually need to turn the machine around so that the back of the disc is facing the direction the airflow is going. That will unload the disc and wash off your rotor speed very effectively. All right, on a windy day. Now, we've so far been talking about avoiding blade flap on, assuming still or very low wind conditions. It's the same thing applies. Obviously, if the wind's blowing over the airstrip, it's the same thing as you moving through the wind to make the wind. So if you've got 8 to 10 miles an hour, then basically you spin up the blades and you just pull them full back, the same as you would if you were doing a still air takeoff run, and wait until the blades come up to speed. Just be aware if you're doing that, if the wind is not exactly 8 to 10 or very consistent, if it's dropping down to 5, they'll actually slow and you run the risk of getting into blade flap there. So you may want to go forward, but if you go forward, you have to be careful that if the wind was gusting, say 5 to 15 miles an hour, and you're trying to maintain 8 miles an hour, and you start taxiing forward at 5 miles an hour, you could have 15, 20 miles an hour airspeed very, very quickly. So you have to taxi very slowly, and you may have to ease the stick back and not pull it full back straight away. Or you can just wait until you've got a good strong breeze, wind up the blades, pull them full back at that point, get enough speed, start moving, and just be aware if a sudden gust hits your face, that could put you into blade flap. You're going to need to be careful of that. You may need to push a stick forward a bit and just check. If the speed is greater than 10 miles an hour, and you are going to have to not pull the stick full back, you're going to have to gradually ease it back and watch the blades accelerate. So if the blades are accelerating, there's no need to pull the stick any further back. So you may have pulled it halfway back to full back stick and the blades are accelerating, leave them there. Don't go all the way back or you'll get them into blade flap. Just leave them. If they're accelerating, they're accelerating. You're not moving anywhere, you're not wasting any runway. So let them accelerate up. Let them accelerate up and then go full back as we're going. In really strong winds, e.g. like 20 to 30 miles an hour, I've found that I can't hand wind in 25 mile an hour winds. Your blades will be flapping at full forward stick because of the disymmetry of lift, and I can't get them fast enough by hand to do that. Won't be a problem with a prerotator, but you have to be very careful. So what I've done in the past is pulled it behind a hanger to get the airspeed to be a bit more choppy and drop down a bit and give me an opportunity to spin the blades up in the 15-mile-an-hour wind and then taxi out once you've got your blades up to speed. And all in all, just be patient. Now, Brian's asked a question. He said, how is flapping during flight different from flapping during takeoff? Well, takeoff is flight, but if you're referring to in flight, you've got a very high rotor speed, and so you will have blade flap happening. What they'll talk about is at very high speeds, you will actually get to a point where the blades can exceed the teeter angle in flight, and that's basically the same problem. So the limiting speed factor on gyroplanes is the teeter angle, because if you exceed the teeter angle in flight, you'll actually get into a similar situation which will just roll you over onto the left. Most people are going to be at high risk of bunting their machine over when they get to those sorts of speeds, but you do have to be very, very careful. It's also a reason why, if you're planning on flying very fast, it's not a good idea to have extremely large blades. The faster you want to fly, you should have shorter blades. The initial lead up to takeoff, blade flap's an issue because your disymmetry of lift, your blades are not fast enough yet. Your blades are going to be really fast at high speed, Brian, but they're not going to be their teetering would be reduced, but eventually your speed gets enough that there's a symmetry of lift takes over and your blades can't flap enough. I hope that answers your question, Brian. Okay, other factors that contribute to blade flap: larger rotors. Longer rotors have more drag, wider chord rows have more drag. They're heavier, so you have to overcome more inertia, and they have greater lift on the advancing side. It needs greater teeter angle to compensate. So obviously longer rotors are harder to wind up. We were test flying the rebuilt gyroglider at Wandai the other weekend, and we had 23-foot blades instead of 22-foot blades. It was actually really hard to wind those blades up because we don't have a prerotator on that, and we had to go up and down the strip a few times before we got the thing. Basically, we had to wind up, jump straight in the seat and go. We couldn't have someone from the car wind them up and run back to the car because the blades had lost too much speed. Greater angle of incidence on the rotors. So angle of incidence being the angle we set to the hub bar, so the angle the blades are set at the hub bar. Now, Benson on his wooden blades was flying 0 angle of incidence, no angle of attack built into the hub bar. 0 to half a degree is what he had. So that diagram above you saw that I showed you before was for 0 degrees angle of attack. So if you imagine another 2.5 degrees, where that rotor disc was 14 degrees, it'd now be 16.5 degrees at 2.5 degrees angle of attack. So a lot of modern machines, they put 2.5 degrees on. That forces you, of course, to have a prerotator, which you would have anyway because you've got a 9-foot mast and you can't reach the blades. But just remember, blade flap is going to be a problem if you've got very high angle of attack on the blades. Benson typically didn't go more than 1.75 on his metal blades because you could still hand wind them at that angle, but anything above that angle you just can't hand wind. It's also going to mean a more difficult runoff. You're going to be overcoming a lot of drag. And in gusty conditions, a little wind is good. A lot of wind can tip the blades winding up to just over the edge. So if you have a good thermal come through, it can send you into blade flap even though you had everything going right. So you need to be aware of those things. So it's why I like open frame gyros. Okay, last little bit. Hinging or flapping. There's terms. The other term that's often used is blade sailing. An argument my CFI had with the rest of the world and lost was that he used to call it hinging and everyone else called it blade flap or blade sailing. Terry, my CFI, lost the argument, but his reasoning is worth understanding. Now, his question was, when you talk about that, he'd say, how do birds flap? How birds flap their wing? What's the image you have in your head? Now, the image you have in your head is something like this. Now, if you've ever built and flown wooden rotors, this thing which Terry referred to as blade flap actually did happen, and it's worth understanding. If you're going over a bumpy grass strip, and most of us were flying off grass strips back in the day, when the machine hits a bump, the airframe gets pushed up, which means that because of the inertia at the tip of the blades, they sort of stay where they are for the time being, but they get pushed up. That's going to give you a negative angle of attack on both blades. Notice there's no difference in the blades, but there's going to be a negative angle of attack. When you come off the bump and go down, because eventually that tip will go up as well, then you get this. And what you get here is a high angle of attack, and you can actually stall out both blades, so you get zero lift over the whole disc, or a highly reduced lift. That means your auto-rotative force disappears and the blades just don't want to wind up. So if you're on really bumpy ground on your machine and the blades don't seem to be coming up, this is why your blades are actually flapping. Notice this looks like actual flapping of a bird's wings compared to the seesawing or hinging that you'd see in what we call blade flap. Now, I would find that on bumpy strips, and particularly with wooden blades, this could happen, and you'd be going, why aren't the blades winding up? You push a stick a bit off the backstop and nothing's happening. They're not they're not in blade flap, but it would often lead to blade flap, so you had to be aware of this. Okay, any other questions? That's the presentation. All right, so Brian's asked a question. If you have time at the end, can you do a brief discussion on the advantages of wooden blades? Yes. One of the main advantages of wooden blades is that because they're set to a low angle of incidence, they need to be set to a low angle of incidence if you're hand winding. If you were winding them up with a prerotator, you could set them to 2 degrees, 2.5 degrees, it wouldn't be a problem. But because they're set to a low angle of incidence, if you're hand winding, they spin up very quickly. And they spin up very quickly from a fairly low RPM. Because you're reducing the in the blade flap, remember, we're not going to stall the blade as quickly because it's going to be harder for it to reach 16 degrees. And when they do spin up, because they chord-wise balance them, instead of having a heavy leading edge going up the blade, so most aluminium and composite blades will have an aluminium extrusion with the profile shape of the leading edge, and they'll either wrap fiberglass around that, or they will glue the skins on aluminium blades onto the back of that. And what that achieves the 25% chord-wise balance. So the wooden blades will be balanced across the width of the blade at the 25%. So 25% from the leading edge, you want it balanced. And that keeps them stable in flight, stops them getting into flutter. So wooden blades don't have that long aluminium extrusion. They're just wood with a thin steel spar going the whole length of the blade with a tip weight. Now that tip weight gives it its chord-wise balance, but that tip weight is about 2 foot in from the tip of the blade, which means it's 32 ounces of lead in there, 25 to 32 ounces, mine are 25 ounces of lead. At flying speed, it means they're producing about a ton of centrifugal force. So wooden blades have a lot more inertia, they're lighter. So my aluminium blades weigh about 25 kilograms. To lift up my aluminium blades onto the rotor head, my wooden blades weigh 18.5 kilograms. And my metal blades are only 22 foot. Once you get up to 23, 25, 27 foot, you're getting up closer to 35, 40 kilograms for a lot of blades. So wooden blades, very, very light by comparison, but they fly heavy, and they're also very flexible in flight. So that makes them, that means that the winding up phase, you have to be a little bit careful of blade flap, but because they're low pitch, they are actually easier to wind up than aluminium blades. Extruded, Brian's also asked another question on this following up. He said, are extruded aluminium blades balanced similar to wooden blades? They should be, and most of them probably are. You'd have to check, but there was one bloke making extruded aluminium blades in Australia. I can't remember the brand name, and I wouldn't mention it for legal reasons, but we tested a cross-section of a set of blades that had been smashed up from those, and we cut off a 2 foot section that wasn't damaged, and we chord-wise balanced them, and they weren't. They were tail heavy, and so at 25% they fell on the tail, and that means that in flight the blades are going to be dynamically unstable. And one guy I knew who had them in his lightweight machine said that when he got to a certain speed, the machine became twitchy and unstable, and that was those blades, and he got rid of those and had to buy another set of blades. So because you're doing the extrusion, you can't have as thin a trailing edge I think the reason a lot of them got away with it was because because the extruded section was so stiff compared to a normal blade, chord-wise. It meant that the blades were overcoming the possibility of flutter, which they get into if they're incorrectly chord-wise balanced. But his did get into flutter after above a certain speed, which is of course not good. But look, if you designed them properly, you could make them so you just needed to have a little bit more weight at the leading edge. But my experience of the extruded blades were very heavy, very smooth on the outside surface. They when the extrusion actually means that the blades they get little warps when they're extruding them out, and what the blade manufacturers would typically do, or the ones I spoke to in Australia, is they would match sets. So you might have a 2-degree warp at the tip on one set of blades, so you get a billet load, like a certain weight of blades, and you would find all of the blades in there that had a 2-degree warp on them, and you would match them together in a set, and then you would build your cluster plates to get the angle of attack right for that. And then you might have another set that were at 0, and you might have another set that were at 1 degree, and you might have another set that were 3 degrees, and so they would just tend to do that. The guy that made my aluminium blades, he would actually he would bend that warp out of the blades. It would take him ages to do that. So yeah, that's that. Any other questions? I'll give you a few seconds. Okay. All right, guys. Well, thank you very much for listening. I'm very sorry for talking over those videos. I had gone to some bother to actually add the sound to those, so I didn't have to do that, and it all worked smoothly. And then I just started automatically going into my teacher mode and started to talk over that. So my apologies for that. I hope you found that useful. The video should be up for anyone who wants to follow through. Thanks for that. Catch you later.